Okay, so let's talk about the setup for logistic regression. We'll start with binary logistic regression here. You have the training data, which is little d-dimensional input vectors along with labels that are binary. Yi's are in 0 and 1. And we start out with a discriminative model. We basically say, I'm just going to assume that the log likelihood ratio, I'm calling it Z instead of L here, just because we use it a lot in the handout, and I'm just going to use, sometimes the term L, sometimes the term Z for the LLR here. The log of the probability of y equals 1 divided by probability of y equals 0, posterior probabilities, is going to be a linear function of a feature vector. And the linear function is based on these weights W, and those weights are to be learned in the logistic regression. What about the feature vector itself? Well, the block diagram that corresponds to this is, of course, as follows. I have X coming in. I have feature computation. That gives me this phi of X, right? Then I apply W to it. I get Z, which is W transpose phi of X, right? It's a LLR. And actually there's one more step I can take after that. We've seen before that if you give me a binary LLR, then I can apply a logistic function to give you the probability that y equals 1 given x, and I'm going to call this y hat, which is sigma of z, or y hat, which is sigma of W transpose phi, right? So let me put a little box around that to show you that this is the model that I get. And basically what I'm saying is, hey, these labels you gave me are actually Bernoulli random variables, and according to my model, for a given model, the probability of that Bernoulli random variable taking value 1 is basically y hat, which is given by this logistic function. As far as the features go, they could be based on your intuition. You could just pick a bunch of features. It could be based on a model, and we saw that for a Gaussian model in which the covariances could be different in different hypotheses, you would have both linear and quadratic terms in the features, or it could be learned. For example, it could be a deep neural network. So there are a bunch of options for that. That part, the learning part of the feature computation, we are not talking about yet. Suffice it to say that this logistic regression box is, by which I mean this part, this is sort of the last box in many machine learning architectures, right? It's sort of the last box in a deep neural network architecture as well. Okay, so within this setup, how would we learn a good model W, right? So how would we learn it from the data that is given to us? So for a given W, what do I have? I have, so given W, we can compute probability of yi equals 1, the ith label being equal to 1, given W, is the logistic function operating on the ith feature vector, where I'm going to now use this abbreviation that phi I is the feature vector for the ith data point, I equals 1 to n. So of course, and I'm going to call this yi hat, right? So given a W, you can compute these yi hats, and then which means of course, that the probability of yi equals 0 given w is 1 minus yi hat. So I can sort of compactly write down the probability mass function for these labels as the probability of yi given w is equal to yi hat if yi equals 1. So I'm going to put this to the power of 1. This is a very standard trick actually for how to write a Bernoulli PMF probability mass function compactly. And it is 1 minus yi hat if yi is equal to 0. And so if I put this down, and of course this formula applies for both yi taking values 0 or 1, right? Because if yi is equal to 1, then it is just yi hat for yi equals 1 and 1 minus yi hat for yi equals 0. And now we can say, okay, now given w, I can write down the conditional probability mass function for the entire set of training data you have given me by assuming that the training data points are independent. So I can basically say that the probability of the data given a particular model w is the product, this is the product, over all training data points of this business, yi hat to the power of yi, 1 minus yi hat to the power of 1 minus yi, right? So remember that I've computed these yi hats based on the feature vectors that I computed from the input data points and all that. So I have the input part is already reflected in this yi hat. And now I'm saying the labels have this distribution, given a model. And so just like we talked about maximum likelihood hypothesis testing, where you sort of try to maximize the conditional probability of the input given the hypothesis, there's also, and I'm not going to dwell on this right now, there's also maximum likelihood estimation, where you're trying to estimate a parameter and you say, I'm going to maximize the probability of the measurements I see given the parameter. So that's what we're going to do here, and we're going to say, I'm actually going to do maximum likelihood estimate of W, which just means, maximize the probability of the data given W over W, right? So that's basically our training procedure. You given the data, you compute something like this, and now you want to maximize this over W. So of course, the moment you see a product like this over a bunch of terms, you will want to take a log and turn it into a sum, right? And the argument of the maximizing value of W is not going to change when that happens. So we're going to do that. The other thing to note is that the probability is here. Let me just change my pen color. These guys are all less than 1. So when I take the log of this, I'm going to get the negative quantity. So instead of that, let me take the negative log of this and get a positive quantity and minimize instead of maximizing. So instead of maximizing over W, the likelihood function will minimize the negative log likelihood, right? That's what we're going to do. And so basically we're going to call this, I don't know, E of W is what I call it in the notes. It's minus log of the probability of the data given W. And now what do I get? I get the sum from I equals 1 to n yi log yi hat plus 1 minus yi log 1 minus yi hat, and of course there's a negative sign out here, and we are going to minimize this. Minimize this. And this is actually actually called the cross entropy between the estimates yi hats and the labels yi. Right? This is a standard term, and you'll often see a deep neural network in which the cost function I'm optimizing with backpropagation is the cross entropy cost function. That's a very common cost function to use when you're trying to do classification. Okay, so we are going to use Newton's method to minimize this cross entropy, and this would be a good time to go check out the video on Newton's method. Assuming you have done so, what we need to do now is to compute the gradient and the Hessian matrix of this cost function with respect to W.